Yes, sir.
We've been talking about how the natural frequency is related to omega naught.
Natural frequency is omega naught.
Okay. In the book, they have where your characteristic
Yeah?
equation, where your S values.
Yeah.
They list that as natural frequencies.
As the S values.
Unless I read it.
They may have called them something else. Can we look at it after class? If you can find it. Do you have your book with you?
Yeah.
Yeah, we'll look at it after class. Show me the specific thing, and then I'll hash it out. Okay. So here's what I want to do today. I want to kind of continue with our conversation about phasors, because I thought we were making some pretty good progress. So just to kind of summarize where we were. Also, where's my notes? So we needed to do a couple of things. So if you recall, a phasor is basically a shortcut for solving a cosine input to a circuit. So we said that when you put in a cosine at some frequency omega, then your output will also be a cosine at that same frequency. The only thing that's going to change is the magnitude and the phase of your cosine. Right? Those are the only two things that can change. And it doesn't matter whether we're talking about voltage or current or where you are in the circuit. Once you're stimulating the circuit with a cosine, everything in the circuit operates as a cosine at that same frequency, right? It all just comes down to magnitude and phase. So the phasor, so basically once you understand that everything's going to look like a cosine, then you don't have to worry about solving that part of the differential equation, right? You don't have to prove every time that you wind up getting a cosine out. So essentially all you have to do is get the phasor for the output and you're done. So we looked at this and we came up with a few interesting things. We said that for a capacitor, that it had, if you stimulate it with a cosine, you can think of this as having an impedance that's equal to 1 over j omega c. That's its complex, that's its phasor impedance. Okay, and I said that can also be written as minus j over omega c. And that can also be written as 1 over omega c angle minus, violating my own rule, minus pi over 2. And we said for the inductor, it had an impedance that was equal to j omega L, which is the same as omega L angle pi over 2. All right? So that's where we started, and then we had this really cool conversation where we said, "Hey, let's find the frequency response of this AC circuit of this this RC circuit." So we had a resistor and a capacitor, and the resistor was, I'm sorry, I keep asking for these numbers. Was it 2 ohms? And the capacitor was 1 farad. And the frequency was, someone must remember, 1 what? 1 hertz? No, let me. Cosine 3t, that sounds familiar, thank you. All right. And if memory serves, we did the following calculation. We said if you're stimulating with cosine 3t, then the voltage here has to be some magnitude cosine 3t plus some phase. And all we had to do is figure out that magnitude and that phase. And to do that, we did it using phasor notation, right? So what we said is that you can think of the resistor as, well, the resistor is easy. That's just an impedance of 2 ohms. We said the capacitor, you could think of it as a phase of, let's see, 1 over j times omega times c. And then what did we do? Does anyone remember? Nobody read their notes over the weekend? Awesome. Voltage divider, exactly. The whole beauty of this is that once you express things as complex phasors, then you just talk about it as a voltage divider. Okay? And the whole problem goes from this nasty differential equation which you've got to solve and you don't understand and blah, 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 and now it's just voltage divider. Right? We simply said that V out had to equal V in, and the phasor of V in was just one angle 0. All right, that's your V in times the impedance of the cap over the impedance of the resistor plus the impedance of the cap. We went voltage divider style on this thing. Isn't that cool? And it works, right? It's just crazy that all that nasty differential equation math. I mean, wait till we get to second and third and fourth order circuits, right? You'll be banging your head against the table trying to do that if you're trying to solve a differential equation. Okay? But if you understand mesh and node analysis, that's it. You can just solve it with mesh and node analysis, except instead of having real valued impedances, you do it with complex valued impedances. But it's all the same math. You can make a computer do it just as easily. Seriously, we'll be doing some of that. Okay, so I believe on Friday we did 1 over, let's see, ZC is 3J over 2 plus 3J. And then I looked deep into your eyes and said, please solve this knowing math that you learned 5 years ago. And you all looked at me like I had 3 heads and nobody knew anything. And I said, please go to your special place and solve this over the weekend. That's 1 over 3J, isn't it? Okay. And we came up with some magnitude and phase for our answer. Okay, and I don't remember. And quite frankly, you should already have it in your notes. Okay. Does anybody have it just off the top of their heads? 0.62, 0.16, angle, negative 1.4 radians. Okay, so that would tell you that your output was 0.16 cosine 3t minus 1.4 radians. Okay, so I want to do 2 things with this just to make sure we've got this put together. And then we'll generalize this. Okay. So when we did the substitution, this is kind of a cool thing. When we did the substitution, remember I said for the capacitor, you can express its impedance like 1 over j omega c, or you can express its impedance as like in the polar notation. So could I have solved this problem if I did it in polar notation? Because I'm telling you, I put equal signs here, right? So this is really the same number as this. So could I have reached the same answer if instead I had written this as V out equals 1 times, let's see, 1 over omega c. So that's 1 over 3 times 1 angle minus pi over 2 over 2 plus 1 over 3 angle minus pi over 2. I mean, that should be the same thing, right? Because I've argued earlier that 1 over 3j is really the same as 1 over 3 angle pi over 2. So supposing I were to do it this way, what I'm trying to avoid is a thing where people say, I don't understand, why did you choose to sub the j notation in? Why didn't you use phasors to solve this? That's what I'm trying to explore, is like why it makes sense to do one method and not another. I mean, this is right. This is correct. How do I solve that now? Divide magnitudes and subtract phases, which is true, but what do I do with that 2? Right, before I can divide, I have to resolve the denominator.
Take the square root of both those numbers squared, so it'll be 2 squared plus squared.
Okay.
Go to that.
And then
That
what do I
gives you- That gives you the magnitudes, and you can divide the 1/3 on top by that.
Right. So what you're saying is that you're basically trying to give me a method for adding those two numbers together, right? So you're saying that I can take the square root of this.
4 plus 1, 9.
What is that? Why can I do that?
Well, that'll give you the complex number, so you can divide the two magnitudes together to give you the 0.16.
Come on. Turns out you can't do that. Here's why it's tricky. So this is subtle, but it's important. When you're dealing with complex numbers, remember we said you can either have rectangular form or you can have polar form. Okay? So 1 over 3j, is that rectangular form or is that polar form? It's rectangular form. Okay? What about 1 over 3 angle minus pi over 2? Polar form. Okay, so that's really the only difference between those two expressions. This is rectangular form. This is polar form. Now, when you're adding and subtracting polar numbers, when you're adding and subtracting complex numbers, which is easier to use? Rectangular or polar? Always. For adding and subtracting, you want to be using rectangular form. Because all you do is you add together the real parts, you add together the imaginary parts. You're done. What about for multiplying and dividing? Which form is easier to use? It's polar form. If you're multiplying or dividing, you want to use polar form. Because all you do is you multiply the magnitudes and you add the phases. Okay? So, now, can you do multiplying and dividing in rectangular form? Of course. It just involves like 8 more steps. Can you do adding and subtracting in polar form? Actually, you can't. You have to convert to rectangular form, add them, and then convert them back into polar form. So, while there's mathematically nothing incorrect about writing this like this, it makes a whole lot more sense to write it like this because I have to add those two terms in the denominator. Okay? And I can't really add 2 to 1 over 3. I can do 2 plus 1 over 3j. That's easy because they're both in rectangular form. But adding 2 to 1 over 3 angle minus pi over 2 is a bit of a mess. Okay? Really the only way to do that is in rectangular form. So what I did was I did it in rectangular form. I multiplied through by 3j. That gave me 1 over 6j plus 1. And now, unfortunately, I'm in this situation where I need to divide. But I just stood here and told you that dividing is really done more easily in polar form. So at this point, if you're doing it by hand, your best bet is to convert, well, the numerator is basically already in polar form. Convert the denominator into polar form and then divide. Or, because this is 2012 and everybody's got a calculator and a smartphone, you just put it in your calculator and, figure out how to make it work. However, at the end, you are going to need your answer in polar form, because polar form is what tells you the magnitude and the phase of your answer. So really, my advice to you is, whatever works, just get comfortable manipulating these numbers on your calculator, okay, or in your computer, because you're going to need to get very good at that. How are we feeling? Good. All right. So let me tie up one more loose end with the simulation. So when we did the simulation, we made our input was a cosine of frequency 3t with an amplitude of 1. So it went from +1 to -1. Did it not? It did. And then we simulated it, right? And when we simulated it, if I remember, we definitely got a cosine with that amplitude, 0.16. Did we not? We got something that looked maybe like this. Okay, where this was, I'm exaggerating a little bit, plus 0.16 and minus 0.16. And we said, yay, we did it, right? But then there was one more difference between the two of them, right? It wasn't just that the height didn't line up. The other thing that didn't line up was remember there was a phase shift between them? A time shift. So there was a delay between the two of them. Does anybody still have written down what the time delay we measured? Spare me having to simulate this thing again. We simulated it, and I remember at the very end of class we wrote down what the time delay was. 40.77 milliseconds. So according to our simulation, we found the time of one of the input peaks. Then we found the time of the corresponding output peak. We measured the time between them, and we got that number. Okay? And the last piece of the puzzle that I wanted to do was to figure out, is this in fact the number that we expected? Okay? Because we got the magnitude right. The simulation showed us a amplitude of 0.16, and that is in fact what we expected. The last piece of the puzzle, though, is to say we were expecting a phase angle of minus 1.4 rads, and what I got was 40.77 milliseconds. And is that the same thing? That's the last piece of the puzzle. Remember when we were plotting cosines a week ago? Y'all were rolling your eyes. Ugh. Okay? Well, now we got to see. Does any of this make sense? Where am I going to erase? Let's erase here. How can I tell whether a phase shift of minus 1.4 radians does in fact correspond to a time shift of 40.77 milliseconds? Divide by 3. So I can think of two ways of doing this. One way of doing this is to do as follows. 0.16 cosine 3, and now I'm going to factor that 3 out of both terms. So if I do that, here I'm going to have a t, and then I'm going to have a, what comes after that now? If I factor a 3 out of the 1.4. Yeah. So 1.4 over 3. Okay, I'm going to get my calculator out. Where did it go? Calculator. 1.4 divided by 3. You're not going to believe this. I'm getting, wait, hold on. You're off by a factor of 100. Factor of 10.
I think
Yeah?
the time we figured out for the time shift was 0.47 seconds.
0.47 seconds?
Yeah. The difference. The time difference.
Ah, the time difference.
Time 1 was 40.77.
Oh, time 1 was 40.77 milliseconds. And time 2 was what?
40.30, and I think it was seconds, not milliseconds.
Ah.
Seconds.
Okay, the plot thickens. Thank you, whoever threw me under the bus. Luckily, I've already forgotten. Wait, hold on. How can this number be bigger than this number? How can this number be smaller?
Oh, then it was wrong. Flip it. Sorry.
It's a week ago, but it should still be in your notes. You don't ball up your notes when you go home. I hope not. Okay, and when we took the difference, we got what? 0.477 seconds? Okay. 0.47, okay, whatever. Okay, good. So, that was the time delay we observed. Now, if I do this, if I factored out the 1.4, and I did it like this, I took 1.4 divided by 3, we got 0.466. Okay? When you write a time delay like this, this is now a time delay in seconds. Exactly what the simulation predicted. So that's how you use that number to your advantage. That's how you figure out the relevance of minus 1.4. That's the easiest way of doing it, by a mile. There's a harder way. And the harder way is not that bad. So the other method is the frequency of this signal is 3 rads per second, which means its frequency in hertz is, it's that number divided by 2 pi. So that's 3 over 2 pi, which means its period is 2 pi over 3. Now, the phase shift is 1.4 radians. Agreed? Now we know in general that 2 pi radians corresponds to 1 period. So, if 2 pi radians corresponds to 1 period, then how many periods does 1.4 radians correspond to? Yeah, we just cross multiply, right? We'll do 1.4 times 1 divided by 2 pi. So the number of periods is 1.4 over 2 pi. So that's the total number of periods that 1.4 radians represents. Okay, so it's that many periods. And how much is each period worth? Each period is 2 pi over 3. So the total time is 1.4 over 2 pi times 2 pi over 3. Wait, that's starting to look pretty familiar. 1.4 over 3. Okay, or you could have just done it the easy way. But it's still nice to see like all the pieces fit together, right? So there you go, 2 ways. So it worked. We should be happy about this, right? With basically no trouble at all, we solved a pretty sophisticated circuit. What do you think? It's good? All right. Now, any questions? We'll stop and take questions before we move on. Okay. Let's prep you for lab this week. We're going to do this problem one more time. Same problem. In fact, I'm going to leave us with the same resistor and the same capacitor. Okay, so let's just stick with R equals 2 and C equals 1. Whatever, it sounds awesome. The difference now is that instead of specifying that my input is going to be a cosine of frequency 3 radians per second, I would like to know how this circuit responds to a generic cosine of frequency omega t. Right, because we just went through a lot of trouble to figure out the system response to a cosine of frequency 3. Now what if I come along and I say, now I want to do frequency 5, and then frequency 10, and then frequency 100? Surely I'm not going to recalculate this thing every time, am I? I mean, that would be a horribly wasteful thing to do. So we're basically going to resolve this circuit, but instead of putting in the specific value of 3, I'm just going to leave this as omega. And then when I'm done and I have my final answer, I can just plug in any old value of omega I want, and I'll have my answer. Are we agreed? Okay. And I want you to keep in mind this one bit of intuition. We talked about this before. What kind of circuit is this? Is this a high-pass filter or a low-pass filter? To remind you, we argued about a month ago that this was a low-pass filter. And I'm going to remind you what the rationale was. And then after we do the math, we're going to prove that we were right. Our rationale was that the capacitor, remember, is I equals C dV dt. If the voltage in the circuit is low frequency, right? If the frequency is not changing, or it's changing very slowly, then dV dt will be, that's a low frequency, right? dV dt will be very small if the voltage is changing very slowly. as it does in low frequencies, then dV/dt will be small, which means I will be small. And if I is small, there's no IR drop across the resistor. And therefore, your output voltage will be equal to the input voltage. So for low frequencies, for low omega, your dV/dt will be small, which means your I will be small, which means that V out will be approximately equal to V in. So at low frequencies, output equals input, or pretty close to it. Then we said at high frequencies means your voltage is changing very, very quickly, which means by definition that your dV/dt is huge. And if your dV/dt is huge, your I is huge. And if your I is huge, that means there's a great big drop across your resistor, because the resistor voltage drop is IR. There's a big drop across I, which means that all your input voltage is going to drop off. It's going to fall off across the resistor, and you're going to be left in a situation where your output voltage will be 0 or close to it. So for high frequencies, you have a large dV/dt, which means your current is large, which means you have a giant voltage drop across the resistor, which means that your output voltage is going to get very, very small, okay, because you're going to lose all your voltage across the resistor. So that was the hand-waving approach. Now we do the math approach. And look how easy it's going to be. I don't mean to say easy to be dismissive. I mean, it's complicated what we're doing, and I appreciate that. But what I mean is easy by comparison to if we tried to do this with differential equations. So I've got V in, I've got V out. I can still get my solution to this using the voltage divider method. Can I not? Let's do it. V out equals V in. What's the phasor of my input? 1 angle 0. It's got a magnitude of 1 and a phase angle of 0. So my input is 1 angle 0. All right, that's my V in. And now I'm going to do the voltage divider. So it's the impedance of the capacitor. What is the impedance of my capacitor? It's 1 over J omega C. Right? I could stick in the value of C if I want, but I'll fill it in a minute. Let's keep it generic now. You notice I leave omega as omega. I don't know what number it is, right? We're going to deal with that at the very end when we're done. Over what? R plus 1 over J omega C. So impedance of capacitor over impedance of resistor plus impedance of capacitor. All right. Now we just got to do math. Now we just have to convert this into a single phasor with one magnitude and one phase. So I'm going to do a couple steps to manage that. So the first thing I want to do is multiply numerator and denominator by j omega c. What's that going to do for me? All right, this is like the standard trick, right? I'm just going to multiply it by 1, right? J omega c over j omega c, isn't that equal to 1? That shouldn't change anything. So if I do that, my numerator becomes 1. My denominator becomes j omega RC plus 1. I just got a little cleaner. You with me? Okay. Be patient, my friends. We're almost there. All right. Now, I got to divide. I got a few options here. I don't like any of them. I think my best bet is to do numerator divided by denominator, and probably the cleanest way to do that is to convert the denominator into polar form, right? Then it's pretty easy to do my division. Because my numerator is just 1, but that's basically 1 angle 0, right? So that's basically already in polar form. So that's good to go. All right, 1 angle 0 and 1, it's the same thing. So numerator is in polar form. If I could just convert my denominator into polar form, the division would be pretty straightforward. So can we convert my denominator into polar form? Sure, right? It's got a real part and an imaginary part. We got a formula for that. Just a few variables. So let's see. If I've got 1 plus j omega rc, and I want to convert it to polar, all right, the first thing I need is a magnitude. What's the magnitude of that expression? Square root of the real part squared plus. You remember the formula? It's the square root of the real part squared plus the imaginary part squared. There's my real part. And my imaginary part, omega rc. It's ugly. I'll give you that. But we can write it. Not that bad. Questions? Okay. What about my phase angle, theta? What's that? Arctangent. Right, so phase angles is always going to be the inverse tangent of the imaginary coefficient over the real coefficient. So imaginary coefficient is omega rc divided by the real coefficient, which is just 1. Ha! All right. So now our total ratio is 1 angle 0 divided by m angle theta, where m and theta are those numbers that I don't feel like writing out again. So remember, that was my V out. All right. Well, now I've got my numerator in polar form and my denominator in polar form. So now, can I get my final answer? Now it's a snap, right? Now that they're both in polar form, I divide the magnitudes, subtract the phases. We're done. Okay, so how can I divide my magnitudes? Simply 1 divided by m, right? 1 divided by m. That's how you divide magnitudes. So 1 over square root of 1 plus omega rc squared. Okay, so that's the magnitude of my output voltage. Angle. Right, and now I take the difference of the phase angles. That's exactly right. So it's 0 minus theta, where theta is inverse tan of omega rc. Holy mackerel. It ain't pretty, but it is right. All right? What was our value for R and C? Have I erased that, or is that still up there? 2 and 1. So if I actually want to sub in my actual values of R and C, I could go one more step and say 1 over the square root of 1 plus 4 omega squared angle minus inverse tan of 2 omega, right? That's what you get when you sub R equals 2, C equals 1. Yes, sir?
Is that only negative when you're dealing with capacitor?
What I'm dealing with?
Capacitor?
Nope. Actually, no. If we switched the capacitor and the resistor, you'd have had a positive. Believe it or not. I don't know, it just works out. I mean, the math is totally different. We can try it, it just works out differently. But if you'd replace this capacitor with an inductor, it would have been positive. How about this? It's always negative for low-pass filters. It's always positive for high-pass filters. There you go. Okay, so fine, that's right, but what does it mean? Okay, like, can we interpret that? I think we can. So, let's try some examples. So let's make a table. Omega, and then V out. So let's say our, how about this? Let's say V in and V out. So suppose for this circuit, our V in equaled cosine of t. Actually, let me do one before that. I'm sorry. Let me try a really low frequency, like 0.1 t. All right, 1/10 of a hertz. A cosine that repeats itself once every 10. No, that's 1/10 of a radian per second. So if I took that cosine and put it through this circuit, what would my output voltage be? How could I figure that out? All I need to finish my phasor here, what's the only thing I don't have? Omega. Okay? So what I'm doing here is I'm saying, okay, what would my output phasor be for that omega? So all I got to do is take omega equals 0.1 and evaluate that phasor. So I'm going to do it over here. So I'm going to say take omega equals 0.1. I'm going to square it. I'm going to multiply by 4. I'm going to add 1 to that. Take the square root. Take the reciprocal. Okay. Can someone tell me what they got for their magnitude? 0.98. Right. I'm getting 0.98 cosine. Cosine what? 0.1 t. Cosine has to have the same frequency, right? 0.1 t minus, let's see here. I'm going to get 2 times omega, and I'm going to take inverse tan, being mindful to make sure that I'm still in radians. I'm getting 0.197. Is that what you guys are getting? Yeah. Okay, minus 0.197. Not a whole lot of radians. Okay? So we're going to play this game for about 5 more, maybe 4 more frequencies. You with me? So let's do this. Let's do cosine of t, cosine of 2t, cosine of 10t, and cosine of 50t. All right, so let's see. Let's divide ourselves up, because I'm not going to do this problem 4 more times. You know what? Divide yourselves up. I don't care how. Somebody do this one, somebody do this one, somebody do this one, and somebody do this one. You're all grown-ups. I'm not going to, you guys be in this group. I'm not doing that. Okay. I'll do some myself, and then we'll, when you think you know one of them, yell it out or just indicate, and I'll see if you're right. Squared 4 times 1 plus. Woo! How are we feeling? We getting some good numbers? I'm going to do a few more calculations myself, and then we'll compare notes. All right. Tell me what you got for the last two.
Cosine of 10, I got 0.00249 cosine of 10t
Point.
minus 1.
Hold on. Slow down, cowboy. I think you're right.
0.00249
0.00249
cosine of 10t minus
1.52. Can we have a confirmation? We'll do this democratically, right? We'll have somebody will suggest that this is the right answer, and then we'll either have an independent confirmation. Let's see if that's what I got. I have no comment. That's not what I got. Oh, let me see.
Yeah, me too. It's not bad.
10 squared. Oh, we have two people saying that's not what they got.
0.050.
Yeah, I got what Nadia got. Okay, hold on. So let's see. 0.049. How about I just say 0.05? Call it a day. Okay, and then what about the phase angle? 0.452? 1.4? 1.452? 1.52. Okay, oh, he was, okay, good. Okay. I'm feeling this one. We'll put a check mark there. Anyone else?
The last one.
You got the last one? Talk to me.
0.1.
0.1?
Yes.
Count your decimal places.
0.10.
No, it's not 0.10. There's no way it's bigger than this one.
0.01.
0.01, that's what I got.
Cosine
Cosine
50t
50t
minus
minus
1.56.
1.56. Can we get a confirmation? We good? All right. You got 2t? Talk to me.
0.243
0.243
cosine 2t minus 1.326.
1.326. Okay, confirm, deny. We're getting a thumbs up. Good.
Yes, good.
All right.
I have the first one.
You got the first one?
Yeah, I got 0.45.
0.45.
Cosine of 1t.
Yeah.
1.11.
Minus 1.11. Nice. Okay. Is this a low-pass filter? Yes. As the input frequency gets higher, omega is 0.1, 1, 2, 10, and 50. As the frequency gets larger, what happens to the amplitude of your output cosine? Smaller, right? Up here, output and input are almost exactly the same. Your input was 1, your output was pretty darn close to 1. As your frequency increases, though, 0.45, 0.23, 0.05, man, now you're practically next to nothing. This is a low-pass filter. All right? Proof positive. You can go to lab. In fact, you will go to lab. All right? You will build this circuit. All right? You will put in a whole bunch of frequencies, and you will validate that in fact you can get something that works out exactly as predicted. Now, in lab, you're going to be asked to make a plot that you're going to make friends with, because you're going to make this plot about 400 times. We'll talk about this in a little bit more detail next time, but the plot is essentially called a Bode plot. Now, Bode plot we can make one Bode plot that plots the magnitudes, and another Bode plot that plots the phases. For right now, let's just plot magnitudes. So, there's a couple ways you can do this. The simplest way is to put frequency on the one axis and basically the magnitude, the cosine amplitude on the y-axis. All right, so in this case, we would do frequency of 0.1 would give us 0.98. All right, so if I put this at 1, this is just a shade below 1. Then we had a frequency of 1, which had about 0.45. Then we had a frequency of 2, which had an amplitude of 0.243. I'm being approximate here. Then I had a frequency of 10. Uh-oh, hold on. 3, 4, 5, 6, 7, 8, 9, 10. And that had 0.0. Oh, good grief. And then I had 11, 12, oh good God. Okay, that's not going to work for me, is it? Okay, what do I do when I have frequencies that are all spread out like this? What's like the standard ninja engineer trick to take all these frequencies? Because God forbid I ask you how this thing responds at a kilohertz. No, sort of. So what do you want me to do with omega axis?
You have to make a gap in it, I think.
Not a gap. Yes! We're going to plot versus log on the x-axis. Instead of plotting omega on the x-axis, we're going to do log omega on the x-axis. Okay? So, presumably at some point someone's, you've learned how to do frequencies on the x. You've learned how to make log plots. That's all you're going to do. Instead of just plotting your omega axis as a linear axis, you're going to get out your little log paper and you're going to do log. Okay? So, let's see. Do I have 60 seconds to explain logs? I'm showing 11:49 on both my clocks. This might have to wait till Wednesday. But essentially, you're going to do a logarithmic axis on your x-axis. Okay? And as it turns out, we're also going to do a logarithmic axis on the y-axis as well. And I'll explain that more on Wednesday. Okay? But there you go. Get yourself a low-pass filter. Thank you very much. Oh, no, we're not doing this on Wednesday, are we? We're having a test on Wednesday. I am so sorry. There is a very good chance we're not going to have the exam in this room. I'm trying to get us a bigger room because it's open book, open note. You can spread your stuff out everywhere. I'm trying to get you a bigger room. So please read your email. Yes.